Nice to meet you, everyone. These are greetings from Switzerland, Zurich. And I'm going to talk about what I call the universal decision machine. I work for a company called Fortum. And Fortum is a big energy company, maybe not so well known by each and everyone. We are basically the third largest one in Europe. We are providing about 10% of the energy needs of Europe. And we are also the third largest CO2 neutral provider of energy in Europe. So we are very ambitious with our goals in terms of providing green energy. And by 2035, the entire asset portfolio is supposed to be CO2 neutral. As you can see on the screen here, global warming, 10 years to go, 11 maybe. That is clearly the purpose behind many things that we are doing. And we're going to look at some of those features first. Energy is one of the main CO2 perpetrators in this world. And it's incredibly important that we are moving away from fossil-based energy production into green energy. And this whole transition is called the energy transition. And the main recipe is, of course, to put more wind and solar in place, but also what's called electrification. And electrification is two components. One is mobility, of course, and the other one is heating. Today, we have around 3% of the cars on the street being electric. And we already see some problems with this when it comes to providing energy. Not so much actually the energy, but the power. And then I mean fast charging. People would like to have their cars charged quickly. So power, exactly when you need your energy, creates a problem for the power grid. It's also the case that on the heating side, many buildings in Europe are still heated by gas and oil. And when that becomes electric as heat pumps, the demand for green electricity is going to increase quite massively. So that means that we have to put a lot more wind and solar power production units in place. And those investments are actually already made. So we know already today that by 2030, we will have 3 times more such capacity available than today. And that means that very often we will actually produce more electricity than we need. And sometimes we will produce a lot less. So that means that very often energy will be for free, but power will be expensive. So if you have no exact demand on when you want to consume it, it's basically going to be for free. But if you know exactly when you need it, you have to pay a lot. So this is the transition we're going through. Investments already done. Wind parks are being built, and you might have heard about even the island that Denmark is now planning to be put between Jutland and England, basically, with enormous amounts of gigawatts of wind being put in place. And all of this is nice, but there is a piece missing. Because if we consider the intermittency, the unpredictability of those energy sources, that needs to meet the demand, the consumption side. And the power grid is such that it needs to be in balance every second. So it's an extremely complex balancing problem, a lot more complex than it is today. And as you can see at the lower left hand of the slide here, that black production, consumption, information meets energy, magic needs to happen. So there's a lot of technology that needs to be put in place to control this machinery. And what I'm trying to drive through here in this talk is that forecasting and optimization is actually all you need. And if you have those two components under control, you have what I'm phrasing a universal decision machine. And excuse me for being a bit cheesy here with the first example here, first of the four, a day in life. You are actually forecasting and optimizing every day, every hour, every minute. So in this case, there is this guy who's going for a job interview, and he's late. He needs to catch a bus across the street. There's heavy traffic. So first of all, he's making a forecast. The risk of crossing the street. He's in a hurry. He might take a bigger risk than normal. He needs to make that forecast. And then based on that, of course, the optimized decision, weighing this risk of crossing and the risk of not getting the job if he's late for the interview. So these are the kinds of problems we are faced with all the time. The more, say, obvious example, medical diagnosis. Objective, diagnose and treat. So what kind of issue is it? Can the machinery, typically machine learning, image recognition or something, identify what the problem is? And then, of course, based on that, find an optimized treatment, conditioned on the patient specifics and the severity of the illness identified. Autonomous driving, I don't think I have to mention that as an obvious case. Get from A to B is the objective. You need to make a lot of forecast of the obstacles that are in your way, and you have to take optimal decisions, again, where you are weighing risks versus costs of delay. So you can see here, it's a lot about managing uncertainties, and very often uncertainties is something that humans actually are rather poor at managing. Another thing they are really poor at is solving huge optimization problems. And the last example here, hydropower plant. In our portfolio, we have 190 hydropower plants distributed across several rivers. The biggest river, there are 36 hydropower plants cascading with a lead time of the water of 4 days from top to bottom. And we need to optimize all of them in one go. It's an enormously big and complex optimization problem. And this needs to be fed with forecast of the inflow, the water in the different catchment areas. That's the fuel. We need to know how much are likely to arrive in the near future, so we can take optimal decisions on when to let the water through, when to dispatch, and in some cases wait if we think the prices are going to be better later. So another view on what I call the universal decision machine is this. It's about enabling things. So if we go back in time and go to 1955, we got what is called the universal computability, so the Turing-complete machine. So it was not really much that was put on the table there. Defined the components of a computer and how a programming language needs to be constructed. But what it did tell was, based on this, push on this, move forward, there will be successful outcomes of the work you put in. It will be useful. Same thing, 1989, where a paper was published around machine learning. The universal function approximator, it was basically proven that with this rather simple neural network architecture, you will be able to approximate any function to any degree. Again, we know by now that this was a lot of problems ahead of you, but still it gave you hope. So keep on pushing. And 20 years later, we saw the first elements of deep learning and all of the many use cases. So it enabled things. And I would propose now that around 2020, we can define a universal decision machine if we combine everything we have in the toolbox to generate forecasts in terms of describing an uncertain future. And based on that described uncertain future, we can define an optimization problem that will lead to optimal decisions. So this is also an enabler. And the world of optimization has developed dramatically the last 10 years. we are now capable of solving much bigger real-world problems than just 10 years ago. And it's the development on the math side that is enabling this. So not so much the hardware and the compute capacity. Of course, we can imagine that once quantum computing is in place with enough qubits, there will be many optimization problems that can be solved much quicker, of course. But it is the mathematics that has developed on the optimization side. And this is a way trying to illustrate this. This is actually Bellman's equations, which is 70 years old. This is a way to discretize your problem and finding a methodology that actually theoretically enables you to solve whatever problem you have. It suffers very quickly from curse of dimensionality, but nevertheless, it is basically a symbol for how you combine forecasting and optimization. So the entire equation here tells you how you go through time steps, discrete time steps, and look at the value of something you decide to do immediately. So the immediate reward based on the state you're in and the set of decisions you can actually take. But this needs to be weighted to the future probability weighted possibilities you might have. So that's why we have a probabilistic future as P, and that is your forecast. And the issue here is that the decisions you take now, so the immediate reward, they have an impact on what decisions you can and should take later. So it's nested in time. So in that sense, it's quite an awkward problem. But the Bellman equation is a very nice solution to it. We are using this one, but we're also using a whole set of other optimization tools, of course. It's mainly to illustrate this very nice marriage between forecasting and optimization that leads to a universal decision machine. So it can be applied to many business areas, of course. Sitting in Fortum, an energy company, we of course focus on managing energy assets. So it can be the big hydro assets I talked about, it can be thermal assets, it can be a huge portfolio of wind and solar assets. But we also now have enormous amounts of energy entities at the edge of the grid on the consumption side. In Germany, for instance, we have 1.8 million photovoltaics on rooftops, actually providing up to 20% of the total energy need in Germany. And we need to be able to incorporate those devices into the total machinery. Otherwise, we are losing control. So that means we need to build an infrastructure, a platform that scales very nicely and can connect to a huge amount of energy entities. We need standardization of the entities. We need connectivity. We need edge data and compute capacity. But we also need, of course, as I am putting in this elliptic red thing here, the forecasting and optimization modules. And here you need to have the full life cycle management of those models. Already today, for just the hydro assets we are now deploying more than 1,000 forecasting models and quite many different ways of optimizing the assets. So of course you need to be able to define the models, calibrate the models, test the models, deploy the models, monitor the models, have all kinds of KPIs running for you, generating reports and telling you what needs to be recalibrated or further looked at. So it's quite a machinery you need to build up on what we call the data science layer. Of course, all these models are completely blind without reliable data. So at the bottom, we have a data management layer as well. Of course, streaming, as we have heard in previous presentations here, and maybe very important for an energy application, event-oriented. There's so much information being received all the time, weather forecast updates, market prices changes, grid congestions to transfer power. And as soon as that kind of information is available, the machinery needs to react by itself. Also, when we are solving these big problems, we're talking about European scale distribution of assets here. This will never be done in isolation. It always needs communication between different stakeholders, so platform-to-platform communication, open standards is a very crucial part of the solution. So here is a bit of the life cycle management, and I already mentioned most of it, but the important thing is here as well that when I talk about forecasting and optimization as a universal decision machine, that means that those two modules, forecasting and optimization, needs to work very coherently, seamlessly together. So we know that on the market there are companies providing a lot of support for managing a large quantity of machine learning models, so the top blue part. There are, of course, the optimization solvers, the providers of those, Cplex, Express, Gurobi. But on the optimization side, you need to put a lot of things together there, not the least digital twins of those objects, assets, environments that you're actually considering when you're solving your optimization problem. So I think we might be a bit unique in the sense that we are putting these two objects together in a very seamless manner. Everything boils down to this for us, this universal decision machine used in the energy transition. We call it an energy backbone. And the analogy is, of course, telecommunication backbones that are there. So we are not only dealing with energy, we are dealing with information, and information becomes as important as knowing how to deal with energy. We're still going to have the big energy producers, so the old ones, but also the new ones, the renewable ones. We need to connect to citizen communities to make sure we have second-by-second understanding of the production, the consumption, and whatever flexibility exists on that side. Flexibility, otherwise, we're typically going to find in the industry side, that's thermal inertia that can be used to postpone or advance a consumption of energy. So that needs to be part of the whole solution. And of course, the electrification on the e-mobility side and heating in terms of heat pumps. So I guess you realize that this is a massive control problem and where we're trying to put the needed infrastructure in place. Thank you very much, and I'm open to questions.